You're listening to China Manufacturing Decoded from the Southeast Group. Hi, back here with you again for the Southeast podcast. It's episode 273 today. Adrian's hosting here and Paul Adams joins me again. So another British takeover. Hi, Paul.
Hello, Adrian. How are you doing?
I'm good. We're both coming live from China. It's been an entertaining time for me because I've been in China for a little bit of time now, with everybody going between the factory, the office, and beyond. And yeah, I mean, wow, what a vibrant place. Everything's going on. We were just looking the plastic injection molding facility that we've got in Dongguan just yesterday, Paul, and new equipment flying in there and some really cool stuff. And the topic today actually is to do with injection molding as well, but not traditional injection molding.
Well, absolutely. Oh, I'm not going to spoil it, but yeah, it's an interesting one. It's a hybrid tooling with steel and resins, let's say.
That sounds pretty new, pretty interesting. So yes, this is worth diving into. And if I was to say that tooling can be 3D printed, maybe a lot of people who this is new to, they'd say, hang on a minute, Adrian, you're crazy. What are you talking about? Because people are thinking hard steel tooling, perhaps most commonly for, really big production runs. We're talking big blocks of steel, hundreds of pounds of weight to them, going into the big injection molding press machines. And that's probably what's in people's mind's eye. So if we're talking about 3D printing tooling, people will be, well, hang on, that's just crazy. That's not how it works. However, this indeed is what we're talking about. And this is something that we call fast iterative tooling, right, at Agilian. And so that's what I'm trying to get into today. So the best way to start off is by doing a short explainer, and then we'll go into more details. Just give us the skinny on that, just a very short explainer to start.
Yeah, sure. So there's a method sort of creating injection molding using 3D printing. Now, we're not talking about SLA or SLS or anything like this. This is more about a soluble resin which we're using, and that's being produced, or the tools are actually being printed on an LCD resin printer, so which is good. But the thing about it is, you can actually print, and I think we discussed this before in a previous episode. If not, we're certainly going to do some more. You can actually print the actual mold itself. Use that mold, the resin mold. I'm talking about a resin mold. You can use that in a conventional injection mold machine with a few caveats. Inject with your production intent polymer, okay, and this includes sort of fiberglass infused polymers, for example. So we're not just talking about careful, so careful. There you go. No, this is pretty rugged tooling, so you can inject with your production intent polymer, dissolve the tool, and then you've got a finished component. Okay, that finished component can then be used to validate your design. And I mean validate for real, because it's literally just come out of an injection mold machine to do whatever you want. Okay, now it's not necessarily what we're actually talking about today, but I want to talk about the hybrid. So, to be fair, let's talk about the conventional way that we are doing tooling. Now, the conventional way to do tooling,
yes,
majority of people know, as you mentioned earlier, Adrian, would be to machine up big blocks of steel, specialized steel for the bolsters or the block work, specialized steel for the core and cavity. This costs a lot of money. It also entails a lot of lead time. We're talking, multiple weeks are running into months in order from, start to finish, sign off. And these are really designed for high volume production. Okay. And this is what your conventional injection mold looks like. Okay. So the hybrid would be, and hold on, before I move into the hybrid, and some of the features on your products may require sliders or lifters or other complex mechanisms inside the tool itself to create certain features with overhangs or gear teeth or whatever the case may be on your particular design. Now,
Yes.
this is where we are talking about adding in that hybrid situation with the soluble resin part. Okay. So eliminate the need for the lifters and sliders, basic. So this is what we're going to talk about moving forward in today's episode. I want to break this down into various different sections of a can, Adrian. And
Okay.
so there's a couple of ways to do this. Now, one is like you validate the design, the look, and the features, and how they should be fitting together. And you can do that with traditional 3D printing, and that's not a problem. But you can't do any validation with that. The next stage is once you've worked out the design that you think, okay, this is pretty close. Let's validate something in the polymer that is designed for production. So there is a way, and this is what we've been talking about with soluble tools. Okay, so and in some cases you can print the tool such that you can injection mold the complete part. In other cases, you don't necessarily need to do that, and it's just maybe where the two parts meet, or they flex together, or as a snap fit, or as a critical assembly feature that is important from a certification point of view, or a how the product works point of view. So you don't necessarily need to injection mold everything. And I think this is where we're going. So what you would do there, you would potentially 3D print the rest of the product, and you would use the soluble tool for the critical parts only. And you would use the injection mold tool to actually inject into the soluble resin tools, dissolve those. So then you've got your production intent critical parts that then can be merged into the other 3D printed parts. So you've got a better idea with respect to how it's actually going to work and function with production designed products. Okay. That's stage 2, which it has been missing in the past. This is where it's a big step forward with respect to this speed of validation and what we're talking about, fast iterative tooling or a fit process. Let's say, always been missing in the past. You see.
And just to clarify, then, what was the alternative in the past? And why is that disadvantageous compared to this?
Well, the process in the past would be having that leap of faith. We've got the prototype materials representing as close as we could get to injected molded parts. But as we all know, a 3D printed part, even in ABS, for example, does not have the same mechanical properties as the true injection molded part. Okay, it just even though it's like the same base polymer, you're not going to get the same performance from a 3D printed part as you would an injection molded part. So this is where the leap of faith comes from with respect to we've done as much testing as we can with like materials. So let's pull the trigger on that tooling. And it's really a case of it's probably better than hope for the best because you've done the best testing that you can. But, say it really is, let's hope for the best because you've done all of the testing to that stage with no certification validation, let's say, with the material that is strong enough that you've designed for the product. That's how everything has been done and is traditionally done these days, let's say. But there is
absolutely
an alternative we're talking about.
Right. So we're talking about an important bridge in this sort of gap between when we're doing our development and prototyping to actually being ready to start validating through the hard tooling and then going into production if everything is if all is well, of course. Right.
Yep. So the next step, you talked about the bridge,
Yep.
prototyping and production. Now, I know that Renault's done something on this bridging in the past, but this is a little bit
Yes.
what I want to talk about now. And this is where we're talking about the inserts earlier. So with the process that I just laid out, in other words, we're using the resin molds for the critical areas only, and these critical areas could be snap bit, they could be teeth with inside a design, they may be some other mechanically strong requirement or whatever the case may be, but you validate that small particular area or areas or two components, three components coming together with the resin tool. Okay. Now, this is where it gets interesting. Okay. Because you've already done your validation with production intent injection molded parts in conjunction with the rest of the design in traditional 3D printed parts. Okay. So you got that hybrid prototype, let's say. Okay. So that gives you a lot greater confidence in order to pull the trigger on steel tooling because you've validated key areas that are questionable until you get the injection molded parts. Okay. So stay with me, guys. Stay with me. So, yeah, this is a bit of a story, but it's a step by step process that is really
That's good stuff.
groundbreaking with respect to getting reliable parts first time from steel parts without actually making mistakes. Okay, in critical areas, and this is the critical area is the key thing here. So we've validated our parts from the 3D printed parts. Okay, and the resin tools. We've got our injection molded parts from there. We validate and everything's good. So we are confident that when we pull the trigger on the steel tool, we're all good. However, okay, in order to make things an even safer route, in other words, eliminate the need for lifters and sliders in the tool, okay, and just go with your basic tool with the core and cavity and the where you've got anything that is critical that could require fine tuning or tool modifications or anything like that. You then create, this is the magic part, a soluble resin insert that goes into your steel tool in a critical area. Okay, let me say that again. Okay. So you got your steel tool, you got your core and cavity, you got your base part in there, but in there, generally you would have some lifters or sliders in order to create a complex feature. Okay. We are not putting the sliders in there to start with or the lifters or anything like this. So we are producing a steel tool that is very basic, open and shut. Okay. So it's a lower cost, lower risk. I think this is more important, lower risk, but we're not using a soluble resin insert in those critical areas. Okay. So what happens now is as the tool closes, we are in full injection mold machine mode. The part is injected. It's still got our little blue resin insert inside that. So what we do then is put the finished plastic part inside dissolvable water tank or solvent tank. That is then dissolved, leaving the final product with the key feature that you can then validate and test with the complete product being injection molded. Does that make sense? If you could follow Adrian, I'm sure everybody can follow it.
Right. Thank you. Yeah. So the significance of this is, while we are still making the hard steel tooling, we are not putting in the final features such as lifters or sliders, and instead we're testing those functions with 3D printed soluble inserts, which can, by their very nature, be produced again and again pretty easily with slightly different designs in order to test these functions. And the relevance of this is cost saving and the ability to test different iterations of the injection molded part or product which wouldn't be possible if the final steel tooling with all of the functionality built into it was made without enormous cost to change the steel tooling, right?
Yeah. I think you hit the nail on the head, because we are still in that fast iterative mode with respect to being able to validate the product. And if there's any changes inside the tool, we're doing it on the soluble resin part and not on the steel tool itself. And what this allows
Right.
to is there's a massive saving on time. Okay, so this is time critical. Okay, now some projects, I would say the majority of products that are being developed, those projects have two criteria: time and cost. Okay, now
Mm,
everybody likes to get to market as quickly as possible, and this cuts the time down tremendously. It also reduces the cost in order to get parts to production as quickly as possible. Now,
mm.
it's like you said, we are talking days instead of months in order
Wow.
to validate a new design. Can you imagine? It's like, oh, right. So the original sort of prototype we thought worked, but now we've got the injection mold part. It's not strong enough, or we need to reduce the size or increase the size, or whatever the case may be. The change is a real challenge when it comes to injection
Mm,
mold tools in steel.
mm,
Is cost, is time. You've got potential witness lines on the part that could be, you know, aesthetically not pleasing anymore, and it's all
mm,
sorts of problems. But it's with this new process, a new rapid iteration that allows you to reduce the cost and certainly reduce the time, because
mm,
every change required. Literally, can you imagine saying, "Oh, you tested everything. It's like at the end of the day, in other words, 5 o'clock in the evening, you got your part. You think, oh man, it's not quite right. First thing in the morning, so you come in at 8 o'clock in the morning, do the design change, okay, on the feature. You print your new tool part. In other words, your soluble resin part. You print that the
yep.
same day, and literally this could take hours. So by 4 o'clock
Mm,
in the afternoon, you're going to send that to the tool guys and say, right, here's the new insert, injection mold that, and the same day you've got your next part to validate.
mm.
One day
I
turnaround.
mean, i in manufacturing, that is lightning fast. So yes,
Oh, do
that's
you know
the
what
ability
I mean?
to
Yeah,
bang out a new iteration
yeah.
daily. That's crazy fast. So yeah, and this is where the hybrid comes in that you mentioned at the start of the episode, because what we're doing, we're taking hard tooling, which intrinsically is not something that can normally be very varied and changed quickly and easily or cheaply. And we're turning it into another sort of tool that we can use to validate quickly. So it's a real sea change there.
Well, it is, and another caveat that we put down here is this is not the final injection mold tool. Okay, this
No.
is the halfway house. This is the bridge solution that we talked about before.
Mm,
And definitely, this is the best of both worlds, because we are getting the steel tool, let's say 80% there. Once we've
mm,
validated the key features inside this, no, you know, let's make one thing clear. We can continue to do this and pump out products in the hundreds, if not thousands. Okay, so this is not just like test one, let's call it a day. No, if we got this
mm.
correct and we got products that need to be sent out for verification, certification, whatever the case may be, long-term testing, reliability testing, ongoing reliability testing, we can still pump out products in their thousands using this particular process. And at some
Mm.
point, then you can say, you know what, now's the time to actually freeze the design. Let's now upgrade the steel tool. Let's put in our specific sliders, lifters, whatever the case may
Yeah.
be, internal mechanisms in order to create this final feature that we have now for
Mm.
sure validated.
Right. And you as the manufacturer then have that peace of mind that you're making that pretty substantial investment into the hard steel tooling, and it's far less likely that you're then going to have to make subsequent changes or anything like that, and then suffer from the time and cost penalty involved, which you were talking about. So, yeah, I mean, it all sounds good so far. The reason we're talking about this, Paul, is because we actually do have this equipment ourselves and we've been using it. But the proof of the pudding is in the eating, isn't it? And
Yep.
you've got some use cases, kind of some examples where we can talk about how this approach has been useful, right? And so we've got the theory down, right? But how has this been used in practice?
Now, bearing in mind that I'm not going to mention any names or products or anything
Sure.
like that because of intellectual property rights. So I have, let's say, adjusted a few things. Okay, such that we
Hmm.
can actually talk about this. So is designer's right to change something. Let's say. So, but
It's all right.
I want to paint the story. Okay, so in this particular case, I'm going to change a few things around, and this is we're going to call it a surgical tool. Okay, we've been developing.
Hmm.
Okay, so I want to set the scene. Can you imagine testing a surgical tool designed in the morning, dissolving the mold by lunch, printing a new version by dinner, and then testing first thing in the morning? So it's a 24-hour cycle, right? You've tested something, doesn't work, redesigned it, printed it, dissolved it, molded it again, first thing in the morning, 24-hour cycle. Okay. Virtually unheard of. Okay. So
Mm.
look at what's a case study, let's say. Okay. So
Hmm.
can you imagine sort of a medical startup is looking for a quick entry to market for their particular products? Okay, and they are
Hmm.
thinking using someone like ourselves in help to help them achieve their goal. But what they've understood is the design has some intricate parts, complex internal channels for fluid delivery, undercuts that would traditionally require sliders and in a metal mold, and it's not a straightforward product design. Okay, because this is a medical device that goes whatever the case may be, but there are
Hmm.
complex components, okay, and channels and snap fit assemblies that are not easy. Okay. So the traditional method, we would actually plan this out, or any contract manufacturer or molder would plan this out and say, okay, no problems. The steel tooling, okay, steel tooling, that's going to take you 60 days to get to T1, 45 days to T1. In other words, is where the tooling is getting their parts out so you can test them. That's going to be like 60 days. Call it 2 months. Okay. Cost 10 to 25, maybe $30,000 US dollars. Okay. Risk. Oh, yeah, for sure. Let's talk about risk. So the potential design flaws that are only discovered after the tool has been completed. Okay. We talked about this before.
Mm.
Yeah. Big risk. So how do you
Mm.
overcome that? So, they thought they had overcome that because they were doing the prototypes and the 3D print and everything looked okay, but it wasn't production intent material. Okay. And this is where
Mm.
the design flaws were shown after the injection mold tool was finished. In other words,
Mm.
$30,000 worth in and 60 days later or 2 months worth later, then only to find that the product doesn't work. Okay.
Wow.
It's what's the solution? Okay. So this hybrid solution that we've been talking about is we have a fantastic opportunity to look at printing multiple iterations of the tool using a soluble mold, a soluble resin mold. Okay. And let's say we do 4 different designs of the critical components or critical areas within the component. Those 4 particular molds could be printed in days. Okay. Call it 1 week. Okay. For just to add a little bit of buffer, call it 1 week. Okay. So we've got
Mm.
1 week versus our sort of steel tooling. We're talking about getting the product correct, ready for validation. Okay, they're already in and the product doesn't work. Okay, we're talking 1 week in, and we've got 4 different molds that we can test because we're not too sure which one of these sort of features are going to really work. So let's do some testing on 4 different times. So okay, we're 1 week in. There are no sliders, no cores, and no lifters or anything. Estimated cost, call it for the 4, call it $800. Okay.
Wow. Okay.
Something like that. Estimate. Okay.
Yeah.
Material testing. All right. So on the original injection mold machine, okay, they were using sort of polycarbonate, a food grade or medical grade polycarbonate. Okay. Didn't quite work. So therefore they had to use an alternative material. Okay. The alternative material had a different shrink rate. A different shrink rate means a different part size when it comes out of the tool. All right. And to remember that different size doesn't fit together. For example, okay, with our 3D printed parts, we said, okay, bearing in mind we've got 4 different tools. Okay, one of them is we can print more than 4, so we've got 4 different designs, and if we want to try 2 different materials, we know the shrink rate, so therefore we could mold another set of 4 to accommodate the shrink rate for the injection mold polymers that we want to test. Okay, so all right, let's call it 8. So we're now for up to $1,600, $1,600, but we're now printing 4 different designs in 2 different polymers. Okay, what they were able to do there is validate the combination that worked best. In other words, design number 3 with polymer number 1. Okay, in 1 week. All right, I'm adding buffer here, but we're doing that in 1 week. Okay, $1,600, 1 week. We validated the product design. Okay, because we were able to test the fit and the function and the assemblability without spending $25,000-$30,000 on a steel tool. Okay, what was the result? Well, the overall result was because if you go to, and this is this is basic where we are, time saving 6 months or more versus traditional tooling. If you start to cut steel, right, you are into a whole world of pain once you start to change. We've already talked about that. Yeah, this can cost money and time and degradation to the tool design itself and the life of it. Okay, cost saving. We went in with 4 molds with 4 different designs. We then replicated those 4 with different polymers. In other words, we accommodated the shrink rate for the different polymers. So we've got 8 different tools. We've done the testing on combinations of the design and the polymers and come up with a final version within 1 week. Okay, so cost saving, let's say that we're into this for $30,000 on the traditional tool. By the time they've done the tool modification, we're talking about another $10,000. Okay, so that's a big chunk of money. Yeah, and bearing in mind that this is a medical product, and there's no messing around. Okay, the outcome, right? The final outcome was that they could actually submit production parts produced in resin tools, okay, and then they done the halfway house hybrid. That's what I was looking for. Hybrid tooling, steel tooling, key areas with the resin, okay, and they managed to get their parts into FDA clearance and other medical certification houses they want a full 6 months before they would have done. Okay,
that's mind blowing.
That to some people is a game changer. It really is a game changer. Yeah, and you've got to bearing in mind that the overall risk has been reduced tremendously. Yeah, so I talked about earlier in a podcast. Majority of projects have 2 criteria that you really focus on. Well, in reality, it's a lot more than that. And risk has to be right up there.
Mm.
So we're talking about
Mm.
time, cost, and risk mitigation. And this hybrid process allows you to compress all of those, or certainly the two of them, and reduce your risk level tremendously. Really does.
Mm. Yeah, and the time, it's just it's not even the financial though. Like as you said, making changes to the tooling. The tooling itself could cost tens of thousands of dollars. Then making changes to the tooling could be another $10,000, and that's the changes that are needed to sort of validate if it needs it. With this, you're talking, a couple of $1,000s to do the same work and a huge saving in time. And for, let's say, hardware startups, it doesn't need to be medical devices even. If you're a hardware startup, no doubt you want to get to market as soon as possible with your, shiny new innovative product, hopefully is what it is,
Yep.
right? Get it, that 6 months, that could be the difference between you really building your own little niche in the market or failing.
Well, that's right. I've got 3 points down here, though. I made a quick note as a closing
Okay.
aspect is really for startups. This is proof of concept without bankrupting the budget. Okay.
Huh.
So that's a really, you can get there without spending too much money. All right. So, which is
Mm.
for startups. From an engineering point of view, you have the freedom to fail fast. Okay.
Mm.
And a failure is part of the game with respect to every single new product coming through a design process. Okay. As long as you fail fast and fail forward, in other words, you learn from those mistakes and corrective actions. And if you can do that quickly, that's fantastic. Okay. And the other one is sustainability, less material waste versus machining molds over and left or right. We've had a case, okay, where the design was thought to be, as in like inverted commas, thought to be mature enough in order to pull the trigger on some tooling. Okay. Inject
Mm.
ordered parts, come back, final assembly, found out the overall product needed massive changes. Now, this was not
Uh-oh.
a case where the tool had to be modified. The tool had to be scrapped and started again.
Wow.
Okay. So you can imagine a $30,000 suite of tools
Mm.
scrapped, start again. That's another 30,000, we're into, $60,000 worth of tooling just to get one part out, your
Mm.
product out. One tool, a suite of tools, whatever the case may be. But the key thing is, you don't need to do that. There are safer ways. Risk reduction, reduced time, or reduced cost. That has to
Mm.
win-win. Has to.
Amazing.
So,
Fascinating stuff. I mean, I'm sold. Listeners listening now, how do you feel about this? Is this new to you, this kind of technology? Do you feel that this could help you? Comments and feedback, absolutely welcome. We'd love to know what people are thinking. We have written about it. We've got some pages about it. So there's even some images of the tooling or the inserts, as Paul mentioned. It's a polymer. They're sort of blue, but yeah, it looks like a 3D printed kind of part, doesn't it? But yeah, they're soluble, meaning that they just dissolve away, leaving something which can have quite a good or complex geometry, which you wouldn't necessarily be able to make with 3D printing. So there's nothing about this that isn't interesting at the moment because it's such an innovative process. So for more learning about that, check out the show notes. There will be links. And if you've got any questions, you can ask us as well. But I think that was well worth looking into, Paul, because this isn't old hat stuff. This is really the technology of the future. This is cutting edge now.
it is, I want to be clear, we're not the only ones doing this. This is not a brand new,
No, no.
but this is pretty leading edge stuff. It's
Mm.
we're right up there on the crest of the wave on this technology, so which is good.
Yeah, it's fascinating to hear how it really cuts out that risk and that guesswork compared to, the way things used to be. So, yeah, really, really good that we've been able to cover that. And I'm really appreciative that you've, been able to share that with us, Paul. So another good one in the books. And I'll be looking forward to next time that you're on the podcast, Paul. And the only thing left to do is to thank everybody for listening. And thanks again, Paul, for guesting.
All right. Thanks a lot. Bye-bye.
Thanks again for listening to this podcast brought to you by the Sophie's Group. We're on a mission to provide you with everything you need to manufacture effectively in Asia, including inspections, auditing, new product development support, contract manufacturing, 3PL warehousing and fulfillment, and much, much more across Asia's key manufacturing areas. Visit us at sofeast.com, that's SOFEAST.com, to learn more and get help. If you've enjoyed the podcast today, please do rate, review and share, because it will really help others discover us too.